So work converts one form of energy into another form of energy. That's the definition of work. And one of the ways that we talk about work is its relationship to kinetic energy. And we're going to find that if net work is done to something, if more work is done in one direction than another, then that's going to add kinetic energy to our system. And so we're going to talk a little bit about what's called the work energy principle, which is this connection between work and kinetic energy. All right. We can also quantify the amount of energy that a system has by adding up the different kinds of energies, right? So here we'll start with kinetic energy. This box is being pushed down a conveyor belt with this applied force. It's got some friction resisting, but it's moving in that distance. And then in the vertical direction, we can kind of ignore it, right? Because we have no movement in the vertical direction, so there's no work. But we've got two forces that are balancing each other. The horizontal work is FD cosine theta. For the applied force here, that cosine theta is 1, so it's just FD. And then we can do a little math magic here. We'll take Newton's second law and one of the kinematic equations. So this kinematic equation is a little bit rearranged, so it may not look exactly familiar, but we move this over here and we have that 2a delta x. And so this is the v f squared equals v naught squared plus 2a delta x equation. We're going to take work here. Newton's law, second law, says force is equal to ma, right? So we put in that ma here. So work is equal to mad. And then we're going to take this acceleration definition in 1D and stick it in here. Okay, so we're just taking, basically we have three equations that we've learned so far, and we're combining them. And we're going to rearrange this, okay? And what we find is that work is equal to, there's that half in here, half mv squared final minus half mv squared initial. And that's the change in our kinetic energy. So what does that mean? Well, it means that this half mv squared term is our definition of kinetic energy. It defines translational kinetic energy. This means it's in a straight line. Okay. If we were to look at the units of mv squared, we would find that it has the same units as energy. What we just went through gives us some sense of what's called the work energy principle. Work results in a change in kinetic energy. And in fact, the net work on an object results in the net change in kinetic energy. Okay, so when we work on a system, like that gravity pulling down the box, or the boulder, or this force pushing this box, when we work on a system, we increase its kinetic energy. When the negative work is on a system, like this friction in the leftward direction, what's the cosine of 180? Well, it's -1. So that's going to remove, it's going to do negative work on the box. It's going to remove kinetic energy. And then sometimes you'll have a system actually doing work, like fluid moving through a turbine. And when it does work, it's going to lose some of its kinetic energy. Now, the key point here is net work. Okay, so in this case, we have an applied force adding kinetic energy, but a friction force removing kinetic energy. If those two forces were equal, then our velocity would stay the same, right? Because we wouldn't have a net external force. We'd have a net external force of 0 in the horizontal direction. That would mean that it's not accelerating. And if it's not accelerating, then its kinetic energy, half mv squared, is going to stay the same. Okay, so there's no work being done on the box, net work being done on the box, if friction and force are equal. The kinetic energy is staying the same, and the net work is equal to 0. That's a tricky point, so we'll work on that uh, as we go through this. All right, so let's test out the work energy principle and see if work does in fact equal to kinetic energy. You can't trust these textbooks, so we got to find out ourselves. So let's assume that at time equals 0, our box isn't moving, and we'll try and figure out what the work and kinetic energy of the box is after they've moved this far. So to calculate the work, we use our work equation. We want net work here because we want to know how much the kinetic energy has changed. So we have an applied force and a friction force. We insert our work equation here, FD cosine theta. For the applied work, cosine theta is 0 in the rightward direction. For friction, the cosine theta is 180, right? Because the D moves in the rightward direction, but the F moves in the leftward direction. Then we put our numbers in here. The distance traveled is the same. The big difference here is our cosine, right? Cosine theta, or 0 equals 1, cosine 180 equals -1. So the friction is doing negative work on the box. And we find that 92 joules of work has been done on the box. Now, our work energy principle tells us that this should be the same as the change in kinetic energy. Now we want to confirm that the net work done, 92 joules, is the same as the kinetic energy. And we have the tools to do that. We're going to use first the Newton's second law to find our acceleration, right? So here's Newton's second law. That are our two forces, right? So this is the sum of forces, 120 newtons applied in the positive direction and 5 newtons of friction force divided by mass, and we get an acceleration of 3.8 meters per second squared. Now we know acceleration, but what we want is our velocity, right? Because that's going to be able to, we'll use that to tell us what our kinetic energy is. And to find final velocity, we're going to use a kinematic equation, right? So we look back at our kinematic equations. We want to find final velocity, and we want something without time in it, right? Who cares about time here? Not us. And so we use this equation. Our delta x is 0.8 meters. We know our acceleration, our initial velocity is 0. And our final velocity is about 2.5 meters per second. Now we can find the kinetic energy of the box at the end of this 0.8 meters. We take our equation for kinetic energy and we put in our values, right? Our mass and our velocity here. And lo and behold, physics holds and kinetic energy is 92 somethings, right? What the heck are these things? Well, let's figure out. Let's take a look at those units. If we take one of those meters from the meters squared and put it outside our parentheses, we have kilogram meters per second squared times m. And if you go back and look at your force notes, you'll recognize this as the unit for force. So this is actually a Newton meter, which makes sense, right? Work is force times distance. And then a Newton meter, as it turns out, is the same as a joule. So the units for energy and work are the same, and the work energy principle holds. All right, see you in class.